Hey everybody. Today we're getting into integration by parts. Definitely the most important technique of integration after u-substitution. The formula is pretty simple. There it is. Fundamentally, we're just doing the product rule in reverse. There's our old friend, the product rule. If we take indefinite integrals of both sides, all we really have to do is to shuffle those terms around to get that formula for integration by parts. Fundamentally, integration by parts helps you when you have an integral of a product where u-substitution isn't getting you anywhere, and in particular where only one of the factors is easy to anti-differentiate. Usually we write the formula like this in a slightly more compact form. Integral of u dv equals uv minus integral of v du, basically just grouping the differential dx along with one of the functions. This all gets clearer when we do an example. Let's do the integral of x e to the 6x dx. It's clearly a product, and a u-substitution isn't going to get us anywhere. So we're going to let u be a function we're going to differentiate, dv be a function that we're going to anti-differentiate, and we'll include the dx with that. I will talk more about how to choose your u and your dv in just a few minutes. For the moment, let's just go with u equal x, dv equals e to the 6x dx. We're going to differentiate u, anti-differentiate dv, and then solve for du and for v. I'm leaving out the plus c here, for the moment at least. The way that we're going to deal with integration by parts for indefinite integrals is just to put in a plus c at the very end to get the most general antiderivative. Now I've got my ingredients. I can follow the recipe for integration by parts there at the top. Integral of u dv equals uv minus the integral of v du. So I get uv is 1/6 x times e to the 6x. And then the integral of v du is 1/6 integral of e to the 6x dx. We've still got an integral here, but now it's a lot more manageable. This one's fairly simple to do. So let's do it. When I anti-differentiate e to the 6x, I get 1/6 e to the 6x. So that's where that 1/36 is coming from. Now I'm going to add in the plus c, the constant of integration, to get the most general antiderivative. It's always a good idea to check your work when you've got an indefinite integral like this. We should be able to differentiate our answer and get the integrand back. So there it is. I use the product rule on that first term. Of course, the derivative of the plus c is going to be 0. Simplify a tiny bit, and in fact, I get the original integrand back. So we got the right answer. Integration by parts is a powerful technique. It can let you integrate things that aren't necessarily obviously even products, in particular functions that we haven't been able to integrate in the past, like the natural log of x. Here we can not anti-differentiate natural log of x, but we can differentiate it. So we're going to let u be the natural log of x to differentiate that, and dv be dx to anti-differentiate that. So we go ahead and carry out the same procedure as before, differentiating on the left and solving for du, and anti-differentiating on the right and solving for v. So we get du is dx over x and v is x. And then plugging into our formula, integral of u dv is uv minus the integral of v du. Overall, x ln x minus the integral of dx. The remaining integral is super easy. Overall, I get x ln x minus x plus c. If I differentiate this, I just get natural log of x. You should check that on your own. Okay, let's talk about actually picking u and dv. Because once you've picked your u and your dv, it's really routine. You differentiate your u, anti-differentiate your v, and plug into a formula. So a couple of things to look out for. You should pick your dv, obviously, as something that you can integrate, because if you can't, then you're going to be hitting a wall very quickly. You should pick your u to be something that gets simpler when you differentiate it. So for example, in the first problem, u was x, and I differentiated it, and I got 1. That's simpler. In the second problem, u was the natural log of x, and when I differentiated it, I got 1 over x, which was easier to manage. There's a list that you can kind of run through, and this is a good rule of thumb. You should go through it in order. First, look for inverse trig functions, and more generally, inverse functions. Natural log falls into that, but let's say it explicitly. If you have logarithms in your integral, you should consider letting those be your u in an integration by parts. After that, algebraic expressions, particularly polynomials. So x falls into that category, x squared, for example. These last two get harder. If everything else fails, you can consider letting u be a trig function or an exponential. If you have to resort to that, things end up being pretty hard. Again, the two examples we've done so far fall exactly into this paradigm. In the first case, we had an algebraic one. In the second one, a logarithm. Things aren't always so simple. You can't always just go through that checklist. Here's a harder example. This time a definite integral. Integral from 0 to 1, x cubed over the square root of x squared plus 1 dx. The whole thing's algebraic, so that checklist we had on the previous slide doesn't really tell us much. So we have to resort to the more general advice. We want to pick u so that it'll get simpler when we differentiate it, and dv as something that we can anti-differentiate. So somehow I'm going to have to anti-differentiate the 1 over square root of x squared plus 1. So I'm going to throw in an x in the numerator because now I can anti-differentiate that with a simple u substitution. That leaves me a u equal x squared. There's two factors of x still remaining. Of course, if I do u dv now, I get the integrand up above. Okay, once I've picked my u and my dv, the next few steps are all mechanical. I differentiate u, solve for du, so I get 2x dx, and I anti-differentiate dv and solve for v. So v is just the square root of x squared plus 1. The way I'm going to deal with the definite integral here is just to put off evaluating the limits of integration till the very end. So I'm just going to apply my integration by parts formula just like I did for indefinite integrals. uv minus the integral of v du. I'm going to evaluate that last integral, and then only once I have an antiderivative am I going to plug in 0 and 1. There's also other ways to do definite integrals with integration by parts. This is the most universal and I think the simplest procedure. So we've still got one integral to deal with, integral of x square root x squared plus 1. That's another u substitution, u equal x squared plus 1 in that case. Overall, I get my antiderivative is x squared times the square root of x squared plus 1 minus 2/3 x squared plus 1 to the 3/2. I plug in 1, I plug in 0, I get 2 minus the square root of 2 over 3, about 0.195.